Next is the combination of capacitors. Now, if we want to combine two or more capacitors, I can combine in the different ways. Like the first diagram here you see, the first capacitor is connected, the first side of the first capacitor is connected to the first side of the second capacitor, and the third capacitor's first side is also connected to the first capacitor's first side. Like this kind of combination is called as parallel combination. So in the parallel combination, you will have 2 points where all the sides of the capacitors will be connected, the left hand side at one point and the right hand side at the another point. This is how you can identify the parallel combination. There is one more way of identifying the parallel combination, is that look, the potential difference across this battery, or the EMF of the battery is V, then the potential difference across this junction will be V. So for each capacitor, the potential difference will be V. So this is how we can identify for the parallel combination. The potential on every capacitor will be equal. Now the second kind of the combination is when you are connecting the two or more capacitor. You can connect the one capacitor's one side to the directly to the battery, and then second side to the second capacitor first side, and then second capacitor second side to the third capacitor's first side, and this is how they are connected. So in basically they are connected in a line. This kind of combination is called as the series combination. Now we can identify the series combination from the diagram, but there is one more way of identifying if the diagram is not clear, is that let's suppose the charge flowing in this battery through this battery is Q. Now this charge will flow through each of the capacitor, right? So it will flow through these capacitors here. So here you will have plus Q charge, here you will have negative Q charge, plus Q charge, negative Q charge, plus Q charge, negative Q charge, so on. So in the basically in the series combination, you can say that the charge on each plate of the capacitor or each capacitor is equal. This is the you can say the property of the series combination. And now there is the third combination where you have both of the combination, the parallel combination and the series combination combined. So there is the third combination. Now how to find out and how to solve these combinations, how to find out the equivalent capacitance, how to calculate the total charge, the total energy stored, we will discuss it. So let's take the first combination where we have the parallel combination. Let's suppose the potential of the battery is V, and let's give the number to the capacitor. Here the first capacitor, second capacitor and the third capacitor capacitance is C1, C2 and C3 respectively. Okay, so then I can say let's suppose the charge flowing through this battery is Q. So then some part of the charge will go on to the capacitor first. Let's suppose the charge on the capacitor first is Q1. The charge on the second capacitor is Q2 and charge on the third capacitor is Q3. Now because charge is conserved, okay, there is nowhere that the charge is coming and going, the total charge which is flowing through the battery will get distributed on each of the capacitor, right? So using the conservation of charge, you can say that the Q is equal to Q1 plus Q2 plus Q3, all right? Then the Q is, now we want to find out, we want to replace this combination with the single capacitor. So basically what we want is that there should be a capacitor which stores the equal amount of charge at the equal potential. Then this capacitor will be called as the equivalent capacitor. Let's suppose the equivalent capacitor's capacitance is C equivalent. Then the charge on this capacitor will be Q. First our calculation is to find out this C equivalent. How to calculate it? The potential of the battery is V. So can I say that C equivalent will be equal to Q multiplied by V? Okay, sorry, Q equals to CV if you apply that formula. So can we say that the Q is equal to C equivalent multiplied by V, right? Okay, good. Let's place it here. So here we have C equivalent multiplied by V equals to Q1. Q1 is the charge on the first capacitor, right? And the potential of the first capacitor is also V. Why it is V? Because it is directly connected to the battery. So whatever there is potential in across these terminals, the same potential will be there through this terminals as well. That's why the potential difference through each of the capacitor is equal to the potential difference of battery in this combination. So can I say that Q1 is equal to C1V? If I do this, then I can replace it, the Q1. Q1 is C1 multiplied by V. Now I can apply the same approach for the second capacitor and the third capacitor. So then I have C2V and the C3V. Alright. Now V is the potential. I can take out common in the right hand side. So here I have C1 plus C2 plus C3 multiplied by V. And that is equal to, in the left hand side, C equivalent multiplied by V. So then V and V will be cancelled out. So basically I am getting the formula or a equation for the equivalent capacitance. Then the equivalent capacitance is, in case of parallel combination, is C equivalent is equals to C1 plus C2 plus C3, and if I have more capacitor 3, 4 or 5, so then I can keep on adding the capacitance. Now this is a kind of formula which we can memorize and we can use in the examination for the parallel combination of the capacitor. We can use it directly. Good. Now I want to find out the next, what is the stored energy, the total stored energy. Alright, so for the total stored energy, we know the energy inside the capacitor stored in the capacitor is half CV square. So the energy in the first capacitor, let's keep it U1, that is the stored potential energy in the inside the capacitor in form of electric field, is half C1 V square. The stored energy in the second capacitor is half C2 V square, and the third capacitor stored energy is half C3 V square. Okay, then we have the total energy stored. So U total of this combination is half. Then half V square you can take out common from each term, then you will have 1 C1 plus C2 plus C3. And right now we did the calculation of the equivalent capacitance, then C1 plus C2 plus C3 can be replaced by the C equivalent. Then the U total, the total stored energy, here I am putting it. So here the total potential energy is half C equivalent multiplied by V square. Alright, so this is our total stored potential energy. Let me highlight it. So basically if you know the equivalent capacitance, you can use it for the energy as well. Alright, now the next is, okay, sometimes what happens in the question, you will not have the 3 capacitor or 4 capacitor, you will just have the 2 capacitor. And sometimes you need to find out what is the charge distribution. Okay, so here we will get some ratio. Okay, so let's find out what will be the ratio of the charge when we take the parallel combination. So let's take only 2 capacitor. Here I am having the 2 capacitor which are connected parallel to each other. Let's suppose their capacitance would be C1 and C2, and they are connected to the V potential battery. Now the question may be, okay, the charge Q is flowing from the battery and they have given you the Q charge. What is the charge on the first capacitor and what is the charge on the second capacitor? Okay, so you can do the calculation, but there can be a direct approach and a formula which you can memorize and you can solve it directly. So look, the V potential in this capacitor and in this capacitor is equal. Okay, so then can we say that the V1 is equal to V2, where V1 is the potential of the first capacitor and the V2 is the potential of the second capacitor. Okay, alright. Now Q equals to CV. From there, the V is Q divided by C, right? So can I replace the V1 with the Q1 divided by C1? Okay, and the V2 is Q2 divided by C2. So here comes our ratio of the charges Q1 divided by Q2 is equal to C1 divided by C2. So what you understand from here is, this is how you can keep in mind that if the capacitance of the capacitor is more, then the charge stored on that capacitor will also be more. Okay, so basically Q1 divided by Q2 is just the ratio of the capacitance. If you have 3, then as well you can use, but this approach will be very good if we have 2 capacitors. Okay, Then I want to find out the Q1. So you can just apply the ratio formula, how to calculate the value from the ratio. So basically you want to find out the Q1. So total value is Q, and now that is getting distributed. So the Q1 ratio is C1. So ratio C1 multiplied by the total ratio divided by total ratio C1 plus C2. This is our the charge stored on the first capacitor. It will be a very good approach to use this formula. And we can also write down the Q2, where Q2 will be C2 divided by C1 plus C2. That is the ratio of the Q2 divided by total ratio multiplied by the total charge that we are going to distribute on the both of the capacitor. Okay, we got it. This is our parallel combination and related calculation. Now move to the second combination. Here we have the series combination, and again I'm taking the three capacitors and the capacitance is C1, C2, C3 respectively. And I did tell you that when they are connected in the series combination, then at the time the charge on each capacitor will be equal. What is mean by that is that you have capacitor and there will be two plates of the parallel plate capacitor. Then one plate will have the positive charge and the another plate will have the negative charge. Of course, you take any capacitor anywhere connected, the both positive charge and the negative charge will be equal in the amount for one capacitor, single capacitor. That's why I have taken here as well. If you look in the parallel combination, if I take this charge Q1, positive Q1, then this is negative Q1. All right, so that's why for if I consider the first capacitor, so if I say the charge is Q plus Q on the positive plate, then there is negative Q on the negative plate. That's clear. Okay, now what I'm saying is that if you take the second capacitor as well, then the charge on the positive plate is plus Q only. Why this is happening? Okay, so we can think it like this, that this charge Q is flowing from this wire. Okay, the electrons are going, let's suppose 3 electrons went, okay, this, sorry, 3 protons, because we are taking the positive plate. So 3 protons went on this plate. Okay, now these same 3 protons will start from here, so that's why it got negative 3 proton, and then again they will be stored on this plate. So positive 3 proton, then negative 3 proton, then they will stored here positive 3 and negative 3. Okay, because the 3 protons will flow in complete circuit, that's why the charge on each plate will be equal. Okay, we got this idea. Okay, so now the first calculation what we want is that to calculate the equivalent capacitance. It means I want to replace this circuit with a single capacitor. Instead of using 3, 4 or whatever the capacitors are there in the combination, I want to use a single capacitor for that. Okay, so look, can I say the potential on this is V, then the potential on this first capacitor, let's suppose that is V1, second capacitor V2 and the third capacitor V3. All right, yeah. So then if I use Kirchhoff's second law, then can I say that the total potential across the terminal is just the sum of the potential V1 plus V2 plus V3, right? What is mean by that? If you don't know the Kirchhoff's second law, you can simply think it like this, that let's suppose the potential at this point you have considered it as 0, and at this point you considered the positive 3 volt, or it was like the battery was of 3 volt. Then at one point you will assume, of course at the negative side you will assume that the potential is 0, then the positive side the potential will be positive 3. Okay, now when we go round in the circle, again if we reach at this point in through this circle round, then the potential again should become 0. It means if the potential rise through the battery is positive 3, then the potential drop through the capacitor should be minus 3. That's why I am saying that the V is equal to V1 plus V2 plus V3. Quite simple, right? Okay, now I have this equivalent capacitance. Using that, can I replace the V? Yes, we can replace it, right? So V can be written down as Q divided by C equivalent. So that is Q divided by C equivalent is equals to V1. So again, we know Q equals to CV, we can apply for any capacitor. So Q equals to CV. So Q is Q for the first capacitor, C is C1 for the first capacitor, and the potential is V1. So V1 can be replaced by the Q divided by C1. Good. Similarly, we can do for the V2, Q divided by C2, and the same approach we can do for the third one. Then the Q will be cancelled out. Then we are getting a very interesting formula again, that 1 by C equivalent is equals to 1 by C1 plus 1 by C2 plus 1 by C3. This is our equivalent capacitance, and this formula is also quite similar to the formula of our equivalent resistance in the parallel combination, right? So these two formulas you can keep in mind, this one and this one. These are the equivalent capacitance. Sometimes they are directly asked in the examination. Now let's talk about the total energy stored. Total stored energy. So one thing is that you can directly put it that our total stored energy will be half C equivalent multiplied by V square, where C equivalent you can calculate through this, and this is how the stored potential energy. Another way is that you can find out using the we can use the each capacitor. So first capacitor's stored potential energy is half C1 V1 square, okay, or we can use Q square, Q equals to CV, okay, Q equals to CV. Then we can replace it with the okay, we can replace the V1 if you want. Q1 is equals to C1 V, of course V1, of course the Q1 is Q only, so I'm just writing the Q, and here we have the V1, so V1 will be basically Q divided by C1. If I replace it, then the potential energy will be half C1, and V1 is Q square divided by C1 square. So here it is cancelled out. Basically you are getting Q square divided by 2C1, right? Like this you can calculate for the second one, third one. So U2 is Q square divided by 2C2, and U3 is Q square divided by 2C3, and just add these potential energies and you will get the total potential energy U, which is basically, you can take out the Q square divided by 2 common, and this is 1 by C1 plus 1 by C2 plus 1 by C3, which is basically 1 by C equivalent. So you are getting the same kind of formula. Here either you can do the calculation from the C equivalent, or you can do the calculation from the individual capacitors. Okay, now here again we are doing the calculation. What if we have two capacitors only connected in the series combination, right? Now here they will not ask the charge, because you know the charge, if the charge is given that Q charge is flowing, then the Q charge will be stored on the first capacitor, and the Q charge will also be stored on the second capacitor at a potential V1 in the first capacitor and at a potential of V2 at a capacitor 2. But in this, what they will ask is that, let's suppose the battery EMF is V, then what is the EMF, or what is the potential drop on the first capacitor, and what is the potential drop on the second capacitor? They will ask this. Okay, so we want to find out the V1 and V2. So first of all, can I say that the V1 is equal to V1 plus V2? All right. And second, can we say that the Q is equal to C1 V1 and Q is equal to C2 V2? Okay, if we equate them, then we are getting C1 V1 is equal to C2 V2. So from here we are getting a formula for the potential drop ratio. V1 divided by V2 is equal to C2 divided by C1. So what do we understand from here is that if we take two capacitor in the series combination, then they will have the same charge stored, and the potential drop on these two capacitors will be inversely proportional to the capacitance. That's why look in this ratio, here the potential is V, and this V1 is proportional to the 1 by C1, and it is proportional to the other capacitor's capacitance. Now we can find out the V1. V1 is, we need to divide the V, total potential of the battery, in the ratio of C2 to C1, and the ratio of the V1 is C2 and the total ratio is C1 plus C2. So basically we got the V1. V1 is C2 divided by C1 plus C2 multiplied by V. So we are getting it directly. Okay, we can use this formula and we can get the potential of the second capacitor directly, and then we can find out the potential of second capacitor, that is C1 divided by C1 plus C2 multiplied by V. We can use these formulas to find out the potential. So these are two combination. What about the third combination when I have something in parallel and series? How to do the calculation for this? So here we have done the calculation for the series and parallel. So we will not do the calculation for the series and parallel. I will just explain you the method how we can approach these kind of questions where you have the both of the combinations together. So here like we have this combination. This is our third combination where you have two capacitors. They are connected in parallel and then they are connected to another capacitor in the series. So what you will do for this is that first you will find out how I can divide this complete circuit in the parts, right? What is mean by that is that look, you have two combinations, only two types of combinations, series and parallel. These are the basic combinations. So you need to find out the part where you have only the parallel combination, right? And then the another part here we have is the only one capacitor, so that capacitor is alone. But if we find out the equivalent of these two capacitor, then that equivalent will be in the series of this third capacitor. So basically this is how you will divide this question. First you will find out the first capacitor and second capacitor's uh, parallel combination, and then this parallel combination plus C3 will form a series combination, and then you can do the calculation of C equivalent, right? And now you can find out the potential drop on the third one, okay, V3. You can find out the potential drop on the equivalent capacitance of the parallel combination. Let's suppose that is V. Now that potential drop will be on both of the capacitor 1 and 2. Okay, if you want to look at the example of this combination, I will give the example in the next video. Okay, thank you.